In this example, we're going to look at an application of a polynomial function. Specifically, we have this function P of V that tells us the power generated by a water wheel in a stream as a function of the velocity of the water wheel, and we're told that the stream is specifically moving at 4.1 feet per second. So the water wheel could be moving a little slower or a little faster than that, and that's what's going to determine the power. The first thing we're asked to do here is to sketch a graph of P over a reasonable domain. So just like with our other sketches, this doesn't have to be perfect. Try and sketch these by hand, and then feel free to go back in and use technology to try to perfect your graph a little or check and make sure that it looks good. So the reasonable domain part, velocity is our input. So we're asking about what values of V are reasonable. I would say velocity can be negative, but I don't think that makes sense here. Negative velocity implies going the opposite direction, and I don't think we're going to have our water wheel going backwards, basically going the opposite direction of the stream. So let's say we only want to see positive V values. I also think that we're only looking for positive powers. I'm not the power expert. There are things in physics that can be negative and sometimes surprise me, but I suspect that that's what we're interested in. So I'm thinking we'll only want to look at quadrant 1. I do have my function already in factored form, so I like that. So if I was trying to think about what are the zeros, I would imagine setting this equal to 0. And I would say, okay, again, don't forget this first factor, 1600V, that will equal 0 if V is 0. So this graph will pass through the origin, and then factor number 2, 4.10 will also be an x-intercept because it makes that second factor 0. And this one, notice, has multiplicity 2. So when we get to that x-intercept, we'll need to bounce off the x-axis. So I'll just say 4.1 is about here. We know we cross through a 0, 0, and 4.10. We also know that if we multiplied this out, it would be cubic. So the degree is 3, which more importantly for the purposes of this, since we weren't asked, that does give me my global behavior. It would be like a y equals x cubed. And then we just need to think about, is it right side up or upside down? This one is slightly tricky because there is a negative on the V, but that gets squared. So it's like we'd have a V times an opposite of V times another opposite of V. The two negatives actually will get eliminated and it'll become a positive V cubed. There will be a 1600 there, so if you're one that likes to keep track of the number, it would be a 1600 V cubed. But just saying V cubed is good enough to get us the correct global behavior. So we'll be imagining that we need to start on the bottom left and end on the top right. I think that does fall outside of our reasonable domain, but I'm still going to use it to get me started. So I'm going to start, and I'm going to come up, and I'm going to hit my first x-intercept. And that first x-intercept had multiplicity 1, so I will cross straight through. And then I'll start to turn around and come back down. And when I get to 4.1, I'm actually going to adjust that a little bit. I have multiplicity 2, so I'm actually going to bounce off and then continue. So that's my initial sketch. I'm going to go ahead and erase the light blue part. That's outside of the domain. I actually would say we probably don't even want this stretch right here, but I'm not going to be offended if you leave it. I'm just thinking that the power increases as velocity increases, and then as the wheel starts to get close to the speed of the stream, it actually drops back down. Maybe it's right. I'm going to take it back and say I don't feel like I know enough to claim. Maybe once it starts getting going, if it manages to somehow get going faster than the stream, that starts to generate more power again. So maybe not. It seems like it might not be practical, but I don't expect you to be experts on the specific application, just to understand the math behind it and do your best with that. Okay, so find and interpret any intercepts of the graph. Okay, so we know what those both are. We already found them, in fact. It's 0, 0, and 4.10. And for interpretation, I would say the key thing with both of those is that P equals 0. So we're saying that if the velocity is 0 or 4.1, no power is being generated, and that's the velocity of the wheel. Or you could even get into it a little more and say if the wheel isn't moving, or if the wheel is moving at the exact speed of the stream, we don't generate any power. So an interpretation should be something along those lines. Go for your complete sentence. Make sure you include the numerical values and the units as always. The last part of this one is to use technology to estimate the velocity that results in the maximum amount of power being generated by the wheel. So we're looking for this point right here, and inevitably when I draw these, it looks like it's sort of in the middle, but actually it generally isn't. It's skewed off a little ways. So let's jump in Desmos and just plug this in and see what it looks like. I've already typed our formula in, but I haven't adjusted my window yet. I know I don't really want to see the negative stuff, so I can shift that over a little bit. And then I probably don't need to see anywhere close to all of this, all the way up to 18. I'm going to try and match a little bit what I had. I'm going to say, okay, my x-axis, the negative one is fine, but let's go out to maybe 6. That should be plenty based on what we had. And it looks to me like I need to catch a lot more y values. I've got that 1600 out in front as a vertical stretch, so that's not terribly surprising to me. So let's see. Oops, if I can catch this. I'm just going to try a 500. I'm going to try 2000 maybe with that 1600. Okay, still a ways to go. Let me move that out of the way. I'm kind of seeing this in the background. This is going up really far. These are a long ways apart still. So maybe we need to try a 10,000. Ooh, it's getting closer. You can see them coming together. 15, really getting close. 20, okay. So we have to zoom out quite a ways, but we're seeing what I had in my picture. It looks quite nice. I think it's a good check. And what I want to know is, where is this maximum? And it's at about 1.3 and then 16,000 some. I'm going to say 1.37 and then 16,000 some. So back to the question. Estimate the velocity. Okay, so we really only need that velocity number. And we said that that was about, velocity is about 1.37 feet per second. Maximizes power. So I did a partial sentence there. But that's what we're looking for, is to make sure you get some units or give me a little bit of thinking about what that answer actually meant. And just to peek back really quickly, remember I was saying sometimes when I draw these, it looks like the maximum is pretty close to the middle, and you can see that it's not quite, right? My picture's maybe not too bad here, but if 2 is roughly in the middle of those two x-intercepts, this should be, well, actually it's a decent ways, right? My graph should maybe look a little more like this, and then flatten out and head up. So those don't tend to happen right exactly in the middle of your x-intercepts the way they do for quadratics.